Hi guys, I hope you're doing well. So we'll talk about exponential and logarithmic models today, and hopefully you can watch this video tonight, and we'll do the homework questions next week. So we've looked at exponential functions, we've looked at logarithmic functions, we've looked at their graphs, but the actual usefulness of these things is in how we can use them to model real life situations. Think of a situation like the population of rabbits that maybe doubles every year or triples every day or something like that, or the population of mosquitoes, or the population of people in the world actually. So all of these things that occur naturally can be modeled, right, using exponential equations or logarithmic equations. That is why, that's a huge pen, that is why we're talking about exponential of logarithmic or logarithmic models. So this lesson is the real reason why we've been studying this whole unit this entire time, because practical applications is what we are interested in, but you can't apply it practically before you understand it completely. So this is the equation for an exponential decay model, exponential growth or decay model, and this A naught represents the initial amount of population or the initial amount of a substance or whatever it is. This A naught is the initial amount. The K represents the growth or decay rate, and the T represents the time that has passed. If K is positive, it's exponential growth, and if K is negative, it's decay. It's a decay function. So some applications include wildlife populations. If the people at the zoo or at the game parks want to figure out how many deer do we have this year and how many do we expect next year, then they'll use a model like this to predict that kind of behavior. Financial investments use this a lot to determine money that you'll get after a given amount of time. If the K is negative, we said it's decay, and that's common in half-life. Half-life is the amount of time taken for a substance to decay to half its original mass. This is common in naturally occurring elements like carbon, and radioactive isotopes. So let's look at some examples. I have a population of bacteria that doubles every hour. Now every time you get a statement like this, right, this statement actually has information. It doubles every hour. That means that after 1 hour, the new amount is twice of the initial amount, right? Because the initial amount was A naught, but the new amount after 1 hour is twice of A naught. And that's already information that can help you find out some of these values in this formula. So let's see. They said it started with 10, right? Express the population of the bacteria as a function of time t. So we know that the A naught is 10, right? If the A naught is 10, we know that after 1 hour it will be twice of A naught, so after 1 hour it will be 20. So let's see. Our equation is supposed to be y is equal to A naught e to the power kt, and what we know is that after 1 hour the new amount will be 20, right? So the new amount is going to be 20 is equal to the initial amount is 10, e to the power k times the time is 1 hour, because 1 hour, after 1 hour it doubles. So I'm doing all this because I want to first find the value of k, and after finding the value of k I can write this function or this equation as just an equation in terms of t. So obviously I'll divide both sides by 10 here, and then I'll end up with 2 is equal to e to the power k. Remember, if I want to find k, I'll introduce natural log both sides, natural log e to the power k, and then I'll have natural log 2 is equal to k, so k is the same as natural log 2. Now my equation becomes y is equal to a naught e to the power kt, but instead of k, I can replace that with natural log 2 times t, right? Natural log 2 times t. That is a logarithmic equation for this function, or an exponential equation for this function, because e is the natural number that is also a base. However, you can think of this differently, because if we're using this formula y is equal to a naught times b to the power t, right? This is also an exponential growth formula, right? If this is a positive number, then it goes up. If it is a negative number, then it goes down. Now they've told us that it doubles every hour, so that means that this has to be 2 because it's doubling, and you know that this is the growth factor, that has to be 2. If it doubles every hour, then our equation will simply be A0 times 2 to the power t. That's an alternative equation that you can use for this function. Now I want to show you something. From this equation, we can actually come to this equation here, because the equation in the previous page was A0 e natural log 2 times t, and I hope you remember that if I have e to the power natural log of anything, right, that is just becomes the value of x. So that e to the power natural log 2 is just the same thing as 2, and then everything else will remain. So I have 2 to the power t and then a0. So I hope you can see that I'm getting the same formula in any case, right? I can get this alternative formula using the other approach, or I can just straight away interpret it and know that it's going to be a0 times 2 to the power t. This, however, is going to be ambiguous sometimes, right? You need to be very precise in your interpretation, and that's why I'm encouraging you to always use this approach that has the exponential letter e. So let's see. These are the two equations we have. It's either 10 e to the power t natural log 2, because we know that the a0 is 10. Sorry, I can substitute this a0 with 10. So, yeah. Because we know what a0 is, so we can always put it in. This should be 10e natural log 2 times t. Because the equations, the question said anyways to express it as a function of t, and I shouldn't have any unknowns in that function besides t. So we're applying that formula. They're asking us to find out how many hours it will take for the population to reach 200. So this 200 is the new y value, and they're asking us for the time, right? In this formula, they've given us the y value as 200, and they're simply asking us for the t. So this is, we'll just go ahead and solve for t. This will be 10e to the power t times natural log 2, and I'll divide by 10 both sides first. So I'll have 20 equals e power natural log 2 times t, and then I'll introduce natural log both sides. Natural log 2 is equal to natural log e power natural log 2 times t, and then I'll have natural log 20 equals natural log 2 times t, and in order to find t, I'll divide both sides by natural log 2 equals t. So my t value is natural log 20 divided by natural log 2, and you can do this on your calculator. Natural log 20 divided by natural log 2. I'm getting 4.3 something. How long will it take the population to reach 200? I'm getting 4.32 something years. Okay, another alternative is to use this formula, right? They're asking us for the time it will take for the population to reach 200, so I'll just substitute into this and try to find the value of t. Divide by 10, divide by 10, 20 is equal to 2 to the power t. Introduce natural log both sides, and then I think you see that you end up still getting natural log 20 divided by natural log 2, and you have to get the same answer, 4.32 years. So you decide which one is easier, but I advise that we stick to this one, because there will be questions that are more complicated if you're using this approach. Okay, let's look at another application or real life model of exponential growth and decay. There are some radioactive isotopes, and you studied about this when you're doing radioactivity or radiation, probably in 8th grade, that decay over time. And this is how we are able to have oil, underneath our earth, and that's why people go and dig for oil, because all of these fossils keep decaying, and as they decay, they turn into that oil. It's a more, involved and complicated process than I'm simplifying it. But basically, carbon-14 has a half-life of 5730 years, and half-life is the time taken for a compound or an object or a substance to decompose to have its original mass. If you died today, the time it would take for you to decompose to have your original mass, if you are all made up of carbon, would be 5730. So they want us to express this amount of carbon-14 remaining as a function of time. So they're basically asking us to write an equation. Now this sentence here, half-life is 5730, has a lot of information, right? It's telling us that after half the time, right? No, sorry. It's telling us that after 5730 years, that is the time, then the amount of carbon left is going to be half of the initial amount. That's what it's telling us, right? But after this time, this is how much is left. Now, you know the equation we're using is y is equal to a naught e to the power kt. I just need to figure out what the k is and then write that equation as a function of time. So I know that after 5730 years, the amount left is a naught over 2. So I'll just substitute a naught over 2 is the new amount, equals a naught e to the power k times the time, which is 5730. This is an equation I can solve because, as you can see, the a naught cancels out, and I'll end up with a half is equal to e to the power 5730k. And I can introduce natural log both sides. Natural log a half is equal to natural log e 5730k, and I'll end up with natural log a half is equal to 5730k, and if I want to find the value of k, it's going to be natural log a half divided by 5730, right? That's my value of k. So my equation should be y is equal to a naught e to the power k, which is natural log a half over 5730 times the time. Now, I want to relate this to the other approach, which I'm going to do here in this alternative. The equation we've come up with is y equals a naught e power natural log a half divided by 5730 times t. I hope you agree that I can rewrite this as a naught e to the power natural log a half, right, times t over 5730, right? And when I have that expression, e to the power natural log a half is simply the same thing as a half, right? It's simply the same thing as a half, yeah. So I have a half to the power t over 5730. And I hope you can see that it's consistent with what we expect, because half-life means that the decay rate, I mean that the substance is decaying or decomposing or decreasing by a half, right? Each time it's decomposing by a half, and that happens after every 5730 years. So my equation, my alternative equation should be a naught, which is the initial amount, times a half, which is the decay rate, to the power t over 5730. This time that passes will always be a fraction of 5730, because 5730 is the half-life. I hope that makes sense. So yeah, this would be the alternative equation. But like I said earlier, please stick to this approach, because in this approach, it's going to be easy to forget this 5730. If you're going at it with this approach, without starting from here, you'll think, well, my equation is supposed to be ab to the power x, right? Or, to the power x, yeah, where x is the time, and you'll say a is the a naught, b is a half, and it's very, very easy to make the mistake of ending here, because, you're thinking that this is the time. This obviously will be forgetting that this time has to be a fraction of the half-life, because it happens every 5730 years that it reduces to a half. Yeah, but just showing you the alternative and knowing that it's an option, I think can be useful. An example, the half-life of carbon is 5730 years. Express the amount of carbon remaining as a function of time. So we did that and we found the equation. Now, this part of the equation, I didn't simplify it completely, but when you take what? When you take this value, natural log 2 over 5730, it will give you negative 0.00121 times t, which is what you're seeing here. 3 zeros, not 1 0, which is what you're seeing here. So don't be worried about this. Okay, so Now they're telling us to find how old the bond is if it has 20% of its original amount. So this already is giving us the new value, right? This is the new value, which is 20% of the old value, right? The new value is 20% of the old value, and 20% is the same as 0.2 of A naught. So I know that my y is 0.2 of A naught is equal to A naught e to the power negative 0.123121 times t, and the A naught cancels out. I introduce natural log 0.2 equals natural log e negative 0.123121 times t. I'll have natural log 0.2 is equal to negative 0.123121 times t. You can just divide both sides by negative 0.121 and get the value of t. So yeah, you guys can finish that part. And even same thing here, the new amount is 0.2 of the old amount equals A naught times 0.5 to the power t over 5730. So you will have 0.2 is equal to 0.5. This is the alternative method, but you don't, I mean, just showing it to you so you know it exists, but don't feel glued to this one. I suggest that we stick to this one. Is equal to natural log 0.5 t out of 5730. If you simplify this, you'll have natural log 2, right, divided by natural log 0.5. You guys go ahead and simplify, times 5730, and you should get the same answer as you got while using part 1. Alright, Newton's law of cooling is very, very useful for scientists that want to figure out the new temperature of an object after it's taken out of a certain condition and put into new surroundings. So Newton's law of cooling, which was obviously invented or discovered or proposed by Newton, states that the temperature of an object is equal to A, where A is the difference between the initial temperature and the temperature of the surroundings, times e to the power kt. K is the constant, the decay constant, because the time is decreasing. T is the time that it takes to reach that temperature, and Ts is the temperature of the surroundings. So obviously this is a formula to model the temperature of an object. And don't get too mixed up into what the formula looks like. We're only focused on using or applying the formula. So if we want to use that formula, we'll start by trying to solve this question. A cheesecake is taken out of an oven with an internal temperature of 165 degrees. That 165 degrees is the initial temperature, right? Or, yeah, initial temperature. Placed into a refrigerator of 35 degrees Fahrenheit. So this is its surroundings, temperature of the surroundings. After 10 minutes, right? After 10 minutes, the cheesecake has cooled to 150 degrees Fahrenheit. So when the time is 10, the new temperature is 150 degrees, right? Now, we're going to first use that information to find the value of K, because that's what you always do in these situations. First, find the value of K. So, the new temperature that we have been given is 150, is equal to A. A is the temperature, the difference between the temperatures of the surroundings and the initial temperature. So that'll be 165 minus 35. E to the power k times t, and that t that gives us 150 is 10 minutes, so that is times 10, plus the temperature of the surroundings, which is 35 degrees. So this we can use to solve. 165 is equal to 150 is equal to 165 is 130 e to the power 10k plus 35. You subtract 35 both sides, and you end up with 115 equals 130 e to the power 10k. Divide by 130 both sides, and then introduce natural log. 115 over 130 equals e to the 10k natural log, sorry. So you solve that and you end up with an e value that is equal to, and you guys can try this, negative 0.00 sorry, 01226, right? That is your k value. That is your k value. After getting that k value, you can rewrite your equation as t at any time t is equal to ae to the power negative 0.01226 times t plus temperature of the surroundings. Now the next one, oh sorry, we're not finished. It still asks us that if we must wait until the cheesecake has cooled to 70 degrees before we eat it, how long do we have to wait, right? So now they're asking us, what is the time if the temperature of the cheesecake has to be 70 degrees? Well, now that you have this formula, right, all you have to do is substitute for 70, right, in the t. 70 is equal to, the A is still the same because it's the difference between initial temperature and temperature of the surroundings. 165 minus 35. E to the power negative 0.01226 times t plus the temperature of the surroundings is still the same. So you solve this equation, and I want to see your work on this. Solve this equation and you should get a t value that is about 107 minutes, right? I'll check your work to see if you solve that out. The last one that we're looking at is logistic growth. Now, logistic growth is like logical, right? Use like sensible or useful growth. If somebody like Solomon wants to do 2 push-ups and double the number of push-ups that he does every day, on the first day he will do 2, second day he will do 4, third day he will do 8. On the 10th day he would have to do 2 to the power 10 push-ups, right? On the 30th day he would have to do 2 to the power 30 push-ups. Those are big numbers. It's not possible for a human being to do that many push-ups. So even if that growth model is going to be exponential in the beginning, it is illogical or it is unrealistic for that model to continue growing exponentially. It has to have some limit or some carrying capacity. There has to be a limit of push-ups that Solomon can do no matter how strong he is. So that is the reason for this logistic growth model, and it's useful for many applications where the population can only grow to a certain size. So in this model, this C is known as the carrying capacity or limiting value. That is the highest value that is possible. So for example, in Solomon's example, maybe his highest value of push-ups he can do in one go is 200. So that will be the carrying capacity. This value C out of 1 plus A is the initial value, and that's the initial value because it happens when X is 0. So I hope you can see if X is 0, this whole thing becomes 1. So what's left will be the initial value. B is a constant determined by the rate of growth and of the model. So let's look at an example. An influenza epidemic spreads through a community of 1,000 people, right? This 1,000 tells you that this disease or epidemic cannot infect more than 1,000 people because there are only 1,000 people in that city or town. So that means that our carrying capacity is this number. They've given us the constant B, so that's nice. Find A if one person is infected with the flu when time is equal to 0. So they're telling us that when time is 0, one person has the flu. This is the X value, this is the f of X value. So let's substitute and see what we get. 1 is equal to C, which is 1,000, divided by 1 plus A e to the power negative B times X, right? I'm not even writing the value of B because e to the power 0 is going to be 1. So I have 1 is equal to 1,000 divided by 1 plus A, and I can cross multiply and simplify and solve, and you'll find that the value of A in this case is 999 people, right? 999. So the next part is asking us, according to this model, how many people will be infected after 10 days? So when the time is 10, what is the value of Y? Substitute in the formula. We are looking for the number of people that will be affected after 10 days. We know C is 1,000. We know A is 999. E to the power negative, the B value is 0.6030 times X is 10 days. This is substitution, and you substitute that even on your calculator and you should get an answer of around 294 people. So I try to keep this video short, but unfortunately, it's still long, but what was said needed to be said. This is your homework that we'll look at on Monday or next time we have class. Bye.